Hey everyone, this is Anirudh from Edureka. In this session, let's have a look at Keras. It is a deep learning framework which is very popular and widely used. Well guys, this session is intended to be useful for anyone considering to kickstart their learning about Keras and need some insight about the framework. So let's check out the agenda for today. Well guys, let's start out by checking out what Keras actually is. Then I'm sure you guys are really curious about the contributors who make Keras what it is. Followed by that, we can check out the models offered by Keras. And once we have understood these models, we'll check out the steps needed to implement a neural network. Lastly, we'll be checking out a very interesting use case and we can summarize the entire thing later on. So the focus is basically on approaching the framework and to find out what it has to offer for all of us deep learning enthusiasts out here. So now that we have established the agenda, guys, let's begin this session by checking out what Keras actually is. Well, Keras is a Python-based deep learning framework which is actually the high-level API of Tensorflow. And now I have 4 major highlights for you guys, so let's check it out from the start. Well, Keras basically runs on top of Theano, TensorFlow or CNTK. Since it runs on top of any of these frameworks, Keras is amazingly simple to work with. You might be wondering why. Well, building models are as simple as stacking layers and later connecting these graphs. Guys, Keras attracts a lot of attention, but why? Since it is open source, it is actively developed by all the contributors across the world and the documentation is nearly endless. Well, we're good with the documentation, but how does Keras perform? Guys, since it is an API which is actually used to specify and train differentiable programs, high performance naturally follows through here. So now that we know what Keras actually is, who makes Keras what it is? Well, we need to check out some of the contributors and the backers to the deep learning framework. Well guys, Keras had over 4,800 contributors during its launch and the initial stages. And now that number has gone up to 250,000 active developers. Well, what amuses me is that there is a 2x growth ever since every year since its launch. Also, it holds a really good amount of traction among multiple startups. Big players like Microsoft, Google, Nvidia, and Amazon actively contribute to the development of Keras. Good enough. So at this point, I'm sure all of you are curious about who uses Keras. Well, Keras has an amazing industry traction and it is used in the development of popular firms like Netflix, Uber, Expedia, Yelp, and more. Well, now that you know, the next time you watch a movie on Netflix or book an Uber, you know Keras is being used. So guys, if Keras is getting all this attention, what makes it so special? What makes Keras stand out among all the top framework? Here I have for you top 10 snippets that makes Keras so special. Well guys, the focus on user experience has always been the major part of Keras. And next, large adoption in the industry, definitely. We just checked out all of the industry traction it gets and this holds well. And next, it is multi-backend and supports multi-platform as well. This helps all the coders come together and code easily. Next up, the research community present for Keras is amazing along with the production community. So this is a win-win for me guys. So what do you think? And moving on, all the concepts are really easy to grasp with Keras guys. And next up, it supports fast processing, which is really good. And guys, it runs seamlessly on both the CPU and the GPU, and it has support for both Nvidia and AMD as well. And the best part for me is the freedom to design on any architecture and then later implement it as an API for your projects, guys. This definitely is a major advantage for me. So next up, for all the beginners, Keras is really simple to get started with, and I'm here to help you guys with this tutorial for that. So stay tuned. And lastly, the easy production of models makes Keras that much special, guys. Now that we know Keras is special, guys, let's dig in a little bit about one of the major concepts which make Keras what it is, the user experience. Well, in my opinion, this is very important for anyone who wants to know more about Keras, or better, they want to start creating their own neural nets using Keras. So clearly, Keras is an API designed for humans. Well, why so? Because it follows the best practices for reducing cognitive load, which ensures that the models are consistent and the corresponding APIs are simple. And moving on, Keras provides clear feedback upon occurrence of any error, and this minimizes the number of user actions required for the majority of the common use cases, guys. And lastly, Keras provides high flexibility to all of its developers. Well, we all love high flexibility, right? So how is Keras doing this? Guys, it's very simple. It integrates with lower level deep learning framework languages like TensorFlow or Theano. So guys, this ensures that you can implement anything in Keras which you actually built in your base language, which is amazing. So next up, we need to talk about how Keras supports the claim of being able to support multi-platform and lets us work with multiple backends. You can develop Keras in Python as well as R. The code can be run with TensorFlow, CNTK, Theano, or MXNet, totally based on your requirement. This almost feels like a tailor-made API for the framework, guys. The code can be run on the CPU or the GPU as well. Support for both the big players being NVIDIA and AMD here. So this ensures that producing models with Keras is really simple. Total support to run with TensorFlow serving, GPU acceleration such as CUDA when using modules such as WebKeras and Keras.js, native support to develop Android and iOS apps using TensorFlow and Core ML, and yes, full-blown support to work with Raspberry Pi as well. So guys, moving on, we need to check one quick concept which forms the backbone as a working principle of Keras. So let's check out a computation graph. Here is an example for you guys. Just before decoding and working our way through the graph, let's look at the features. So guys, do note that computational graphs are used for expressing complex expression as a combination of simple operations for Keras to work with. It is mainly useful for calculating the derivatives during the phase of backpropagation, and hence it makes it easier to implement distributed computing on the whole. So all it takes is to specify the inputs, outputs, and to make sure that the graph is connected throughout. I hope you guys know what a connected graph is. So let's check out our graph. We'll be working away from the leaf nodes to the top. So guys, here as you can see, E equal to C multiplied with D, where C is equal to A plus B and D is equal to B plus 1. So all we're doing is we're making sure we land at E equal to C cross T, which is the head of our tree, and we get to this by performing two operations on the leaf nodes. So as you can see, working down further, E equal to A plus B into B plus 1 actually makes sense now. And in our case, A and B are inputs. So guys, it is as simple as that. So next, let's dive a little bit deeper and check out the two major models, guys. So the first model is a sequential model. The working is basically like a linear stack of layers. So the first thing that comes into my mind when I think about the layered approach is the sequential model. It is majorly useful for building simple classification network and encoder-decoder model, guys. And definitely yes, this is the model which we all know and love. So here we basically treat every layer as an object that feeds into the next layer and so on. And now in the simple code, we'll import Keras into Python. We define the model as sequential, and with the hidden layers, we have 20 neurons and we'll be using ReLU here. ReLU is rectified linear unit, guys. It is one of the activation functions we'll be using. Well, model.fit is used to train the network. Here, by epoch, I'm sure all of you guys are familiar with it already. So it is basically the forward and the backward pass of all of our training examples. And batch size is really straightforward as well. It is the number of training examples in one forward and backward pass, guys. So higher the batch size, the more the memory you'll need. So next, we need to check out the functional model. It is widely used and it holds good for about 95% of the use cases. Well, imagine the concept of playing with Legos, guys. I'm pretty sure most of us have played with Legos in our childhood. It's pretty much the same here as well. Well, the highlights of the functional model is that it supports multi-input, multi-output, and an arbitrary static graph topology. We have branches, so whenever we have a complex model, the model is forked into two or more branches based on the requirement, guys. The code which we have here is pretty much similar to the previous one, but with subtle changes. We first import the models, we work on its architecture, and lastly, we train the network. Well, with functional models, we have this concept called as domain adaptation. So guys, what we did until this stage is that we train a model on one domain but test it on the other. This definitely results in poor performance on the overall test dataset because the data is different for each of the domains, right? So what's the solution for this? Well, we adapt the model to work on both the domains at the same time. And guys, we'll be looking at a very interesting use case using the functional models in the upcoming slides. So stay tuned for that. So moving on, we need to understand about the two basic types of execution in Keras, deferred and eager execution. It is also called as symbolic and imperative execution as well. Well, with deferred, we use Python to build a computation graph first like we previously discussed, and then this compiled graph gets executed. Well, with eager execution, there is a slight change, guys. It is here that the Python runtime itself becomes the execution runtime for all of the models. It is very similar to execution with NumPy. So if you're familiar with NumPy, then it's a cakewalk, guys. So on the whole, here is a quick note. Symbolic tensors don't have a value in the Python code as of yet, but eager tensors will have a value in the Python code. And with eager execution, we make use of a type of recurring neural networks called as trees. So guys, it is basically a value dependent dynamic topology structure. So what are you guys thinking about Keras at this point? Well, it is actually really easy to grasp, guys. Well, next, let's look at the steps needed to implement our own neural network using Keras. There are 5 major steps here, guys. So starting out, we need to prepare the inputs for the model. We do this by analyzing our requirements and specifying the input dimensions. Well, as you know it, the common inputs are images, videos, text, or audio based on your model requirement. The next step is to actually define the artificial neural network model. Here we do everything from defining the model architecture to building the computation graph and also defining the style we'll be using for the model. It is as straightforward as that. Well, step 3 is to specify the optimizer. Think of it this way, a neural network is just a complex function. We need to simplify the process of making the machine learn. Well, the optimizer is just for that. There are many types of optimizers such as SGD, which is stochastic gradient descent. We have RMS-prop, which is based on root mean square, and ADAM, and so on. And the next step is to define the loss function. So for every step in our training, we'll be checking the accuracy of prediction by comparing the obtained value with the actual one. We check for the difference between them and we print out the loss, guys. Well, the goal is to actually define a function which we will use to reduce the losses in each pass of the training phase. There are many types of loss functions such as MSE, which is mean squared error, and we have cross entropy loss, which is also called as the log loss in most cases, and so on. And the last step is to actually train the network based on the input data, which is also called as a training data. And after training, we will need to test the model based on the trained data to check if the model actually learned anything. So it is as simple as this, guys. What do you think? I would love to know your views on this, so head to the comment section. Let's have an interaction there. And now, guys, let's spice things up a bit. I'm sure you guys were curious about the use case, so let me walk you through the entire thing. Well, we'll be checking out a wine classifier in this use case, so let's begin by checking out our problem statement. So we're trying to predict the price of a bottle of wine just by knowing the description and the variety of wine. Well, we can work this out with the Keras functional API and Tensorflow. We'll be building a wide and a deep network using Keras to make predictions for us. Well, can we achieve this goal? Yes, we can. This is a problem statement suited for wide and deep learning networks, as I mentioned. Well, it involves textual input and there isn't any correlation between the wine's description and its price. Well, this is what makes it fun in my opinion, guys. So next we need to check out the model. A lot of Keras models are built using the sequential model API as I told you earlier. But let's make use of the functional API for our use case. Well, true, the sequential API is still the best way to get started with Keras. Why? Because it lets you define models easily as a stack of layers like I explained earlier. However, the functional model allows for more flexibility and is best suited for models with multiple inputs. So we need to know a little bit about wide and deep model, guys. Well, wide models are models with sparse feature vectors. Well, what I mean by sparse feature vectors is that it consists of mostly zeros and a little bit of ones. And deep networks are networks which do really well on tasks like speech and image recognition. So now that that's sorted, we need to take a look at the dataset. Well, for this case, we'll be using a wine dataset from Kaggle. So what's the data? Well, it's basically 12 columns of data and it's as follows. Here we'll be talking about the country that the wine is from. Next up is description, a few sentences from the sommelier describing the wine's taste, smell, look and feel. A sommelier is a person who is a professional wine taster, guys. Next up is designation, the vineyard within the winery where the grapes that the wine has been made from. Next up is points, the number of points that the wine enthusiasts rated the wine on a scale of 1 to 10. However, they only say that they post reviews for the wines which scores greater than equal to 80. Next up is price, the cost of the bottle of the wine obviously, followed by province, the province or the state where the wine is from. Next up I have something called as region 1. Well, with region 1, it's the wine growing area in a province or a state. Let's say for example India. Next I have region 2. Well, sometimes there are more specific regions within a specified wine growing area. For example, we can say Bangalore, India. But this value can sometimes be blank as well. Next up is taster's name. Well, as it suggests, it's the name of the person who tasted and reviewed the wine. Taster Twitter handle for the person who tasted and reviewed the wine. Well, the title of the wine review, which often contains the vintage if you're interested in extracting that feature. Variety, the type of the grapes that is used to make the wine. Let's say, for example, Pinot Noir. That's a type of the grape. And finally, the winery that made the wine. Guys, the overall goal here is to actually create a model that can identify the variety, winery, and the location of a wine based on the description alone. And this dataset offers some really great opportunities for sentiment analysis and other text-related predictive models as well. So now that that's clear, we need to take a look at the sample data case. So here we have a description for the wine such as scent, if it's tart, firm or needs more decanting, etc. So this forms our input for the model, guys. And the output our model provides just from all of this textual information is the pricing that it predicts. How cool is that, guys? So basically we need to check out some of the prerequisites before jumping into the code. Since you're working with Python, we'll require pandas, we'll require NumPy, scikit-learn, and Jupyter Notebook. So yes, Keras works on top of TensorFlow, so we'll require both Keras and TensorFlow to be installed on the machine. So now that that's done, moving on, let's look at a small piece of code. Here are all the inputs that we'll require to build the model. And lastly, we test the presence of TensorFlow by printing the installed version. Well, without TensorFlow, it wouldn't make any sense. So we go to Kaggle and download the data and end up converting the data to a pandas data frame, guys. Well, that's good enough to start. Let's look at the code for this model. I'll quickly open up Google Colaboratory, which is basically a Jupyter notebook hosted on their Google Cloud. You can actually do this on your local machine as well by installing all of the frameworks that I've previously mentioned. So let me go ahead and open Colaboratory and let's begin, guys. So guys, we'll be executing each of these blocks and we'll be going on from there. So let us check out the first block. So here we import all of the modules that we require. So guys, let me run it. And that's done. So next we'll need to install the latest version of TensorFlow. Well, with Google Colab, it doesn't require any extra setup, so it's pretty much straightforward. So guys, that took about 2 minutes and TensorFlow is installed. And as I explained before, we need to import the models that we'll use to build the model. And after that, we'll actually run the code to check the version output of the TensorFlow that we just installed. And the output we're supposed to be expecting is version 1.7 because 1.7 is the TensorFlow version that we installed. As you can check out the output, you have TensorFlow version 1.7. So beautiful. So moving on, we need to download the data, which is from a CSV file hosted on the cloud. So let's go ahead and do that. Now that it is downloaded and ready, let us convert all the data from the CSV file into a pandas data frame as I mentioned. So now that that is done, let's go ahead and mix up the data by shuffling it. And yes, so let's start printing samples from our data set. So we'll be printing the first 5 rows, and as you can see, all the columns that we discussed earlier from country, price, province, all the way till a detailed description of the wine is present here. So now that that's done, next we need to do some pre-processing to limit the number of varieties of wine in the dataset. So let us go ahead and set a threshold of 500 in our case. So anything less than 500 will be removed from analysis in our model. We'll be replacing it with NaN, which is not a number, instead of letting it to be blank. So let me go ahead and run this. So now that that's done, the next step we need to do is actually split the data into a training dataset and a testing dataset. So let's go ahead and do that and print the size of both the training dataset and the testing dataset. So let me go ahead and run this code for you guys, and there it is. We have the training dataset size and the testing dataset size. Now that we have the size, we need to actually extract the testing and the training features and all of the labels. So let me go ahead and run this code and we can actually get the labels. And so that does it. The training and the testing features and the labels are known to our machine by now. So now it's very obvious that we're using a test description. Well, instead of looking at every word that we have found in our description in our dataset, let us limit our bag of words to, let's say, top 12,000 words in our dataset. So guys, don't worry, there is actually a built-in Keras utility for creating just this vocabulary. This is considered as wide because the input to our model for each description will be a 12K element wide vector with zeros and ones, indicating the presence of word from our vocabulary in a particular description. Well, Keras has some handy utilities for text pre-processing that we'll use to convert the text descriptions into a bag of words. With the bag of words model, we'll typically want to use only a subset of all the total words that we found in our dataset. And in this example, I used 12,000 words, but this is a hyperparameter that you can tune. Well, you can try out a few values to see what works best on your dataset. Well, we can use the Keras tokenizer class to create our bag of words vocabulary for us. So let me go ahead and run this to create the tokenizer. Guys, so now that that's done, we'll be actually using text to matrix function to convert each description to a bag of words vector. So let me go ahead and run it. Well, now that that's done, guys, in the original Kaggle dataset, there are about 632 total varieties of wine. To make it easier for our model to extract the patterns, we did a bit of pre-processing to keep only the top 40 varieties. Well, around 65% of the original dataset or 96K total examples. Well, we'll use a Keras utility to convert each of these varieties to integer representation. And then we'll create 40 element wide one-hot vectors for each input to indicate the variety. So let me go ahead and run it, guys. So now that that's run, guys, at this stage, we are ready to build our wide model. Well, guys, Keras has two APIs for building the models, the sequential API and the functional API. The functional API gives us a bit more flexibility in how we define our layers and lets us combine multiple feature inputs into one layer. It also makes it easy for our wide and deep models into one when we're ready. Guys, with the functional API, we can define our wide model in just a few lines of code as you see. Well, first we need to define our input layer as a 12K element vector, well, for each word in our vocabulary, and then we'll connect this to our dense output layer to generate the price prediction. So let me go ahead and run this. Well, now that that's done, we'll compile the model so that it is ready to use. If we were using the wide model all on its own, this is when we'd actually start training it with the fit function and evaluate later with the evaluate function. Since we are going to combine it with our deep model later on, we can hold off on training until the two models are combined, which is done later, guys. So let me go ahead and execute this so we define our wide model. And yup, our wide model is done. Let's go ahead and print out a summary from the wide model. Well, now that we have a summary, we can realize the total number of trainable parameters and non-trainable parameters. Well, in our case, the non-trainable parameters are 0, guys. So guys, that's the end to the construction of the wide model, and it's time to build our deep model. So let's go ahead and check that. Well, to create a deep representation of the wine's description, we'll represent it as an embedding. Well, there are a lot of resources on word embeddings, but the short version is that they can provide a map word to vectors so that the similar words are closer together in the vector space. Well, to convert our text descriptions to an embedding layer, we'll need to first convert each description to a vector of integers corresponding to each word in our vocabulary. We can do that with the handy Keras text to sequence method. And now we've got the integerized description vectors, we need to make sure that they're all the same to feed into our models. Well, Keras is fancy and it has a handy method for that too. We'll use pad underscore sequences to add zeros to each description vector so that they're all the same length. Well, in this case, I used 170 as the max length, so no descriptions were cut short. So let me go ahead and run this. Well, with our descriptions converted to vectors that are all the same length, we're ready to create our embedding layer and then feed it into our deep model, guys. So let's start building our deep model. Well, there are two ways to create an embedding layer. We can use weights from the pre-trained embeddings as I previously explained, or we can actually learn the embeddings from our vocabulary. Well, it's best to experiment with both and to see which performs better on your particular dataset. Here, we'll consider using learned embeddings. Well, firstly, we'll define the shape of our input to the deep model. Then, we'll feed it into the embedding layer, and here I'm using an embedding layer with 8 dimensions. Well, you can experiment this with tweaking the dimensionality of your embedding layer as per your choice. And the output of the embedding layer will be a 3-dimensional vectors with the following shape. Well, it'll have a batch size, a sequence length. Well, in our case, the sequence length is 170. It'll have an embedding dimension. It is 8 in our example. And in order to connect our embedding layer to the dense, fully connected output layer, we actually need to flatten it first. So let's go ahead and define our model and then we can flatten our layer. Well, once the embedding layer is flattened, it's ready to be fed into the model and to compile it. So let's go ahead and compile it. And now that the compilation is done, as you can see, the loss function we've used in this case is MSE, which is mean squared error. The optimizer we'll be using is Adams and the metrics is accuracy. And at this point of time, we have established the wide model and the deep model. So once we have defined both our models, combining them is really easy, guys. We simply need to create a layer that concatenates the output from each of the model and then merge them into a fully connected dense layer, and finally define a combined model that combines the input and the output from each one. Well, obviously, since each model is predicting the same thing, which is the price, the outputs or the labels from each one will be the same. Also, guys, do note that since the output of our model is a numeric value, we will not need to do any pre-processing and it's already in the right format as well. How cool is that? Well, that's done, guys. It's time for the training and the evaluation. Well, you can experiment with the number of training epochs and the batch size that works best for your data set. Well, this is going to take some time, so I'll save you the pain by fast forwarding this a bit. So guys, as you can see, the training is actually done. So each of the epoch took about 100 seconds and we had 10 epochs for the same. So guys, here's the important thing that you have to notice. With every epoch, we were actually reducing the loss all the way from 1100 to 130, guys. And the accuracy of prediction went from 0.02 all the way till 0.0994, which is almost zero point 0.1. Well, wow, that's definitely a breakthrough for just 10 passes, guys. And now that the training is done, it's time to evaluate it. So let me go ahead and run this piece of code for you guys. So that was quick. That took only about 5 seconds and we have evaluated the model. And now it's time for the most important part, guys, seeing how our model actually performs on the data that it has never seen before. To do this, we'll actually call the predict function on our trained model and we'll be passing it our data set. So let's go ahead and do just that. Well, now that that's done, we'll have to compare the predictions to the actual values for the first 15 wines from our test data set. So guys, as you can see, we have a set of predictions from the description and the predicted value is about $24 while the actual value is $22. Next up, we have $34 as a predicted one while the average is 70. Well, this is not a really good case, but okay, that's tolerable. And next up, we have predicted 11.9 when the actual value is 12. Wow, that is actually really close. So next up we have 15.7 versus 9. Well, this goes on and on for the first 15 and it's actually really good. Well guys, pretty well it turns out that there is some relationship between a wine's description and its price. Well, we might not be able to see it instinctively, but our machine learning models certainly can. So lastly, let's compare the average difference between the actual price and the model's predicted price. Well, the average prediction difference is about $10 for every wine bottle. Wow, that is really nice, guys. Well, to wrap this up, let's head back to our presentation and we can run through what we did in the entire session. Well, we started out to check what Keras actually is. Then we checked out the contributors who support and develop Keras. Next, we checked out the specialty of Keras by highlighting some of the really good features. And next, we checked out the models. And next, we checked out the easy steps to implement a neural network. And lastly, we went through this amazing use case and dived right into the heart of Keras. Well, Keras is lovely and I can't begin to tell you how much I'm liking it. Well, that is it for the small session, guys. I hope you took away some real good points from here and that this helped you kickstart your Keras learning. Well, we do have in-depth tutorials on our channel for you to learn about TensorFlow, so make sure you check that out. So thank you guys, you know what to do. If you have any queries, leave a comment and subscribe to our channel for more information on the latest technology and the courses offered.
I hope you have enjoyed listening to this video. Please be kind enough to like it, and you can comment any of your doubts and queries, and we will reply them at the earliest. Do look out for more videos in our playlist and subscribe to Edureka channel to learn more. Happy learning!